Namaskaram. In this session, we will see the relation between linear transformation and basis. In first module, we have seen the coordinate of a vector. That means, suppose we have a vector space V, and V is a basis containing n vectors, and this small v is an arbitrary element from this capital V. Then we know that every vector can be uniquely expressed in terms of basis elements. That's why we can be written as c1 v1 plus c2 v2 etc plus cn vn. And these unique scalars are called coordinate of the vector with respect to the basis. If you consider another basis, then automatically the coordinate is different. Okay. Anyway, we have all these things in first module. Consider a linear transformation from a vector space V to W, and V is an arbitrary element. This is our vector space, and we choose an arbitrary element small v from capital V. Okay. Then what about T of V? We know that every vector V can be written as linear combination of basis elements using its coordinate. So we can write this V as C1 V1 plus C2 V2 etc plus Cn Vn. Okay. Then what of this? What is this T of V? Then using the linearity property of T, we know that T is linear. So we can write this as some C1 times T of V1 plus C2 times T of V2 etc plus Cn times T of Vn. Okay. This is because our T is a linear transformation. And we know that T of U plus V equal to T of U plus T of U plus T of V, and T of alpha U is equal to alpha times T of V. Using these two properties, okay, this is T of U plus V equal to T of U plus T of V. Using these two properties, we can expand this is like this. First of all, we consider this as U and this as V, right? Then using the linearity property, what happened? This is T of C1 V1 plus T of C2 V2 etc plus Cn Vn, correct? Then again, the first term you can apply the second property. So this becomes C1 times T of V1, right? Plus again you can consider this first term is U and the remaining are V. Again you use the first property. Then what happened? This is T of C2 V2 plus T of the remaining term. Again you can use the second property on this term, and again using the same similar again you apply these properties, you can ultimately get T of C1 V1 plus C2 V2 etc Cn Vn is equal to C1 times T of V1 plus C2 times T of V2 etc plus T of Cn times T of Vn. Okay, then what is the meaning of this expression? This means that a linear transformation is completely determined by its action on basis. Why? If you know the values, suppose you know these values, first value, this is our second value, etc., nth value. Suppose you know the image of first basis element and image of second basis element and image of last element. That means suppose you know the images of basis elements, then you can find image of general element. That is the idea. That means if you know the images of basis elements, that is v1 v2 vn etc vn, then you can find image of general element. How? You take the general element v, then first of all we have to write this v in terms of basis element. That is possible. Okay, in a vector space it is always possible, and this is unique. Then using this as expression and the property of linearity, we can write T of v as c1 times T of v1 plus c2 times T of v2 etc plus cn times T of vn. Okay, so that's why a linear transformation is completely determined by its action on basis. Okay, consider this problem. Find the linear transformation T from R square to R cube such that T of 10 is given, that is 201, and T of 01 is also given, minus 134. Okay. Okay, here our T is a transformation from R square to R square, and it is given images of these two elements, let it be E1 and E2. And we know that, what about this collection E1, E2? We know that this is a basis, right? We have seen this is a basis. So in this case, it is given that what is the action of this transformation, linear transformation on a basis, that is given. Our aim is to find, we have to determine the linear transformation. We have to determine the linear transformation means we have to find what is the image of an arbitrary element V from this R square. Okay, suppose this is our arbitrary element V. So we have to find this image, that's all. That means T is completely determined. So what is our, so if V belongs to R square, okay, this V belongs to R square, right? V belongs to R square. So what is the general form of V? We know that every vector in R square is of the form some AB, right? Like a tuple or a pair of two elements. You can write this is a column matrix. You can write this as a column matrix. So then, okay, so what is our first step? First step is we have to express this V in terms of this E1 and E2, right? This is possible. Why? Because we know that this V is a basis. That's why this is possible. So first of all, we have to identify this C1 and C2, or simply say that the coordinate of V with respect to this basis. So what is C1 and C2? Okay, that means our V, that is AB equal to C1 times C1 10 plus C2 times 01. Then this is C1 plus the first coordinate is C1, right? Second one is 0 plus C2, that is C2. Then you can compare the corresponding terms. So what about C1? So C1 is nothing A and C2 equal to B, right? Okay, now we are ready to find the image of an arbitrary element V, T of V. What is T of V? T of AB, right? And we know that this AB can be written as C1 times. What is C1? C1 is nothing A. So A times or E1 is 10 plus C2, that is B times E2 is 0 1. Then using the linearity property, we can expand this as A times T of 10 plus B times T of 0 1, right? It is given that T of 10 equal to 201 and T of 01 equal to minus 134. You can substitute these two. Yes, so T of V is equal to A times our T of 10 is 201 plus B times T of 01, that is minus 134. And you can simply add the corresponding terms. So what is T of V? That is, yes, 2A minus B, and this is 0. So this is 3B, last one A plus 4B, right? So this is the image of an arbitrary element. So the image of this V is 2A minus B, 3B, A plus 4B. That means T is completely determined or completely described. So 2A minus B, 3B, and for A plus 4. Okay. So this is possible only when if you know the images of a basis elements. The advantage of this concept is if you know the images of some elements means a basis elements, then you can find images of any element using our non-values. Okay, that is the advantage of this concept. Okay, next problem. Find the linear transformation T from R square to R square such that T of 1 1 equal to 5 6 and T of minus 1 1 is equal to 3 4. Okay, so here our set is 1 1 and minus 1 1, and we know that this set is a basis. Okay, we have seen this example in I think in first module. So anyway, we know that this is a basis, or it is very easy because this set is a subset of R2, and we know that R2 is a vector space with the dimension 2, right? And what about these two sets? Let it be F1 and F2. Is it independent or not? Yes, they are independent because one of them is not a multiple of other, so they are linearly independent. And this is a two element set, a two element linearly independent set, and dimension is 2. Then we know that such set spans that vector space. So anyway, it's a basis. Okay, so it is given the action of the transformation on a basis. So you can easily find what is the image of a general element. So let V be our general element from R square, and we know V can be written as some AB. So next procedure is, what is our next step? We have to write this general element AB in terms of these two elements 1 1 and C2 into minus 1 1. Okay, then solve this C1 and C2. Okay, and this becomes C1 minus C2, and second one is C1 plus C2. Then you can equate these two, the corresponding terms. So C1 minus C2 equal to A, and C1 plus C2 equal to B. Then you can solve these two. you simply take if you add these two equations, then this become 2c1 equal to a plus b. So what is c1? Similarly, you can find c2. Okay, so how to find t of e? That is t of ab. That is equal to t of c1 times 1 1 plus c2 times minus 1 1, and c1 is a plus b by 2, c2 is equal to b minus a by 2. Substitute everything. Okay, so using linearity property, this become a plus b by 2 into t of 1 1 plus b minus a by 2 into t of minus 1 1. Now you can substitute this t of 1 1 and t of minus 1 1 using given values. So this become, so a plus b by 2 into, what is t of 1 1? That is 5 6, and t of minus 1 1 is 3 4. Okay, you can expand this you can expand this matrix. So this become, with the first term is 5a plus 5b plus 3b minus 3a, and second term is by 2, and second term is 6a plus 6b plus 4b minus 4a divided by 2. On simplification, this become a plus 4b and a plus 5b. So this is the image of general element. Okay, if you choose our general element t of ab, then what is t of ab? T of ab equal to a plus 4b and a plus 5b. Here, yes, t of ab equal to a plus 4b and a minus a plus 5b. And this is your homework. Thank you.